Okay, in this podcast we're going to talk about electrolysis, and hopefully you have watched the video from Mark Rosengarten to understand how the electron flow works and what's happening. So an electrolysis process, the word electrolysis, means lysis means to split. Lysis or lytic means to split, and electro means using electricity. So we're splitting something. So if we take the sodium chloride compound, we can actually split it into its metals and get that explosive sodium and the gaseous chlorine out of that. So it's used to produce pure metals or pure elements from their ores, and it's also used to for electroplating, for putting a thin film of a metal on a substance, either to protect it or to make it, or for cosmetic purposes, to make it look more attractive, like it would be used in jewelry. So there's a lot of differences between an electrochemical cell and an electrolysis cell or an electrolytic cell. And the biggest one is that the electrolytic processes are not spontaneous. They require you to use a battery, and that battery provides power to allow this breakdown of products into their elements to occur. Okay, so it's not spontaneous, requires energy, a battery, DC input to make this happen. Okay, so it involves a negative cell potential as opposed to a positive cell potential in the electrochemical cell or the voltaic cell. And because it's not spontaneous, that would suggest that delta G is positive. Okay, so just from a term standpoint, batteries supply current, an electric current, and that is measured in amps, and an amp is nothing more than a coulomb per second. So it's talking about that flow of electrons and how fast that flow is moving. So if we compare a voltaic cell versus an electrolytic cell, a voltaic cell is spontaneous, an electrolytic cell is not spontaneous. A voltaic cell generates voltage, generates electricity, where an electrolytic cell uses that electricity. It requires a battery or an energy input. When you see a voltaic cell drawn, it happens in two different containers, whereas in a electrolytic cell, everything is happening in one container. Both electrodes are in the same container. They're split in a voltaic cell. The cathode is the positive electrode in a voltaic cell, where the anode is negative. And the big difference that takes a little bit of thinking to remember is that they're opposite in the electrolytic cell. So there's this mnemonic EPA, electrolytic is positive anode. Okay. Important to note that the term cathode and, of course, anode are defined by where either the reduction or oxidation take place. So if you think about the cathode is defined as the electrode where the reduction occurs. So in both types of cells, both voltaic and electrolytic, reduction does occur at the cathode. Okay. Now, in one case, the cathode is positive, in the other case, the cathode is negative. Okay, so most of the electrolysis problems that you're going to see on the AP test involve some stoichiometry and just applying the information. Sometimes you'll be asked to predict the products, and if you are, and there's no water, it's going to be what you would expect. The cation is going to be reduced. In this case, the Na plus goes to Na0, Cl minus goes to Cl0. The anion is going to be oxidized. But if water is present, it is possible that the water gets reduced or oxidized instead. It's competing with the compound that's in there. And you'll see this sodium chloride is liquid because you have to actually get it molten in order for it to be mobile and move and do things. Okay. If you are performing electrolysis of water, which occurs in an acidic solution, the reaction at the anode is the oxidation reaction, and the reaction at the cathode is the reduction. Now, you can try to memorize these products that you get, but what you'll see is these are actually on the reduction potential table. So it tells you exactly what they are, and it tells you what the voltages are. So if you sum up what's here, you will see that this is the overall reaction, breaks into hydrogen and oxygen, and that you have a negative potential, a negative voltage, which is what you would expect in an electrolytic process. It requires energy to make this happen. Okay, so when we look at electroplating, as we will in the lab, what happens is, let's say I have a ring, and I want to make the silver plating. Okay, what I would do is I put the silver, a bar of silver, as my anode, right? I put silver nitrate or a silver salt, aqueous solution of silver, in here, and what happens is the electrons are going to come out of the silver bar, causing the electrons to travel up here. It releases the silver plus ions. The electrons flow this way, right? So the electrons are coming down, and the silver plus ions are attracted to that buildup of negative charge from the electrons, and that silver plus and the electrons make a silver atom, and that silver atom plates onto that ring. Okay? So that's basically what's happening. The electrons are flowing this way. Okay? Still flowing the same way as an electrolytic cell or an electrochemical cell, from anode to cathode. Okay? So as you do that, the silver gets used up. So at the anode, the silver is going to silver ions, right? Silver ions going into the solution, and electrons which are traveling up through the current. On the cathode, you have the silver plus ions that are in the solution picking up those electrons and becoming a hunk of silver, silver metal, which is plating onto this ring. Some of the requirements for electroplating are you need a solution of the plating metal, so we need this silver nitrate solution because we've got to have these silver ions that pick up the electrons to plate. We need to have the anode made of the plating metal, so in this case we have a plate of silver because that's the stuff we want to end up on the ring. The cathode is the object to be plated. It could be a ring, it could be whatever object you want to coat. And you need a source of current, so you have to have a battery or electricity provided in some way. Okay, so let's take a look at a few electrolysis problems. So the first one is, how many seconds will it take to plate out 5 grams of silver from a solution of silver nitrate using a 20 amp current? Alright, so I'm just going to use, so there's a lot of these kinds of questions from electrolysis. Most electrolysis questions are going to be stoichiometric questions, okay? So if I have 5.0 grams of silver, what I know is that 107.87 grams of silver is 1 mole of silver. Okay, and I know that 1 mole of silver let me write the equation. Silver plus 1 electron is going to make silver metal, right? So 1 mole of silver provides 1 mole of electrons, and what I know is 1 mole of electrons is 96,500 coulombs, and because I got 20 amps, remember amps are coulombs per second, so I've got 20 amps, so that's going to be 20.0 coulombs in 1 second. And if I plug and I chug, I end up with 223 seconds, and from a sig fig standpoint, that's 220 seconds, because I've got just 2 sig figs in my grams. Okay, here's another one. In the electroplating of copper, a half a Faraday of electric charge is passed through a solution of copper sulfate. And what mass of nickel is deposited? So remember, a Faraday, a half a Faraday, so a Faraday is the charge associated with 1 mole of electrons, right? Alright, so if I have a half a Faraday, so nickel plus 2 electrons. I don't know why it said, oh, this should be copper. And I got the copper equation. Okay, so if I have a half a mole, 0.500, Faraday, and what I know is 1 Faraday is 1 mole charge associated with 1 mole of electrons, and I have 2 moles of electrons in 1 mole of copper, and that in 1 mole of copper I have 63.55 grams of copper. That gives me 15.9 grams of copper. Okay, let's do another one. We want to calculate the number of grams of aluminum produced in 1 hour by the electrolysis of molten aluminum chloride if the electrical current is 10 angstroms. So here I'm going to have Al plus 3 electrons is going to give me aluminum. Okay, so I'm going to start with the fact that I have an hour. So 1 hour, and what I know is 1 hour is 60 minutes, and 1 minute is 60 seconds, and I got 10 amps, right? So in 1 second I have 10.0 coulombs, right? Amps are coulombs per second. I can use Faraday's number, 96,500 coulombs is 1 mole of electrons, but I have 3 moles of electrons per 1 mole of aluminum. Okay, and I want grams, so 1 mole of aluminum is 26.98 grams. So if I plug and I chuck, I end up with 3.36 grams, 3 sig figs of aluminum. Alright, we're going to stop there.